Welcome to lecture 15b on finding eigenbases.
Recall the definition of an eigenbasis for a square matrix. An eigenbasis does not always exist, but if it does, it is a set which is a basis for Rn consisting of eigenvectors of the matrix A. Last time we looked at this matrix, we see that these three vectors form a basis for R3, and all of them are eigenvectors of A. So this set is an eigenbasis for A. Last time we talked about how eigenbases can be used to speed up multiplication. It is especially useful when you have a high power of a matrix. Here's an algorithm for finding an eigenbasis. We start with an n by n matrix. We find all eigenvalues of A by factoring the characteristic polynomial. This is the first step. And then for each eigenvalue, we look at the eigenspace and find a basis for that by using the fact that the lambda eigenspace is a kernel of this matrix. So this is the second step. And after that, you put all of the vectors you get from step 2 into this set. And if there are n many vectors, this set would be an eigenbasis. If there are fewer than n vectors, then no eigenbases exist. This algorithm constructs a linearly independent set. Let's do this algorithm for this particular matrix. We will try to find an eigenbasis, or we will discover that it does not exist by following this algorithm. The first step is to write down the characteristic polynomial of the matrix A. We get this determinant, which is the determinant of this matrix. To compute this determinant, we do the product of these two entries minus the product of these two entries. So my characteristic polynomial is x squared minus 4x plus 3 minus 1. So this is the characteristic polynomial. Next, I need to find the roots of this polynomial. I don't see an easy factorization, so I can either use the quadratic formula or complete the square. I'll use the quadratic formula. The roots are the negative of -4 plus or minus square root of 16 minus 8 divided by 2. So I get 2 plus or minus square root of 2. So I get exactly 2 roots. So this tells me that the eigenvalues of A are 2 plus square root of 2 and 2 minus square root of 2. I have done step 1, find all eigenvalues of A. Next, I will do the second step, which is to find a basis for each eigenspace of A. First, I will find a basis for the eigenspace corresponding to eigenvalue 2 plus square root of 2. This is the same as finding a basis for the kernel of A minus 2 plus square root of 2 times the identity matrix. First, let's compute what this matrix is. So I have A minus 2 plus square root of 2 identity. So I get this matrix, and to simplify, I have this -1 minus square root of 2 and 1. And on the second row, I have 1 minus square root of 2. To find a basis for this kernel, I need to first solve this matrix times mystery vector equals the 0 vector. So I take this matrix and put it here, and then add the 0, 0 for my augmented matrix. And I will row reduce until I get a row echelon form. First, I see that the second row already has 1. So I think I will just swap the first and second row. Because this entry is a leading one, I will do a row operation so that this entry becomes 0. This is my new second row, but let me now simplify this expression. This is the same as 1 minus the square of square root of 2 plus 1. So I have 1 minus 2 plus 1, which is 0. So this entry is 0. So I see that my second row is all zeros. I also see that I have arrived at a row echelon form. Since the second column has no leading one, I will let the second variable, in this case y, to be a parameter. Next, I do back substitution. This first row is equivalent to this equation. I will then plug in y equals t into here, and I will get an expression for x. X is -1 plus square root of 2 times t. So I get a general solution where the first entry would be x and the second entry is y. I can then write this as a linear combination where t is a coefficient. So I can take this vector and this will be a basis for the eigenspace of A for this eigenvalue. So we have a basis for this eigenspace. Next, we will do a very similar computation for finding the lambda 2 eigenspace of A. So we find a basis for the kernel of A minus the second eigenvalue times the identity matrix. So this matrix looks slightly different than in the previous slide. I have this matrix, and to solve, to find a general solution for elements in this kernel, I take this matrix and add the 0, 0 to turn this into an augmented matrix. And then I do very similar row reduction steps until I arrive at this row echelon form. I see that the second column has no leading one, so I let y be a parameter. I take this first row. This is equivalent to this equation. And I replace y with t. So I then get x is equal to -1 minus square root of 2 times t. I then get the general solution where I just take x and put that into my first entry and y put that into my second entry. I take t out and I have this vector. I can take this vector to be a basis for the lambda 2 eigenspace of A, where lambda 2 is this number. The last step in the algorithm to put all vectors from step 2 together into a set. If there are the same number of vectors as the width of the matrix, then that set is an eigenbasis. Otherwise, the matrix has no eigenbasis. So I take the two vectors from step 2. There are 2 of them, and the width of the matrix is 2. So this set is an eigenbasis for A. In this exercise, I have a different 2x2 matrix, and I want to either find an eigenbasis for this matrix or say that it does not exist. You should use the same algorithm we just used, algorithm 2. If you're watching this, I encourage you to pause the video and try to do this exercise on your own. The first step of the algorithm is to find the characteristic polynomial of A and compute the roots. To get the characteristic polynomial, I compute this determinant. So I do x minus 1 times x plus 1 minus 1 times -1. So I get this polynomial, and after I simplify, I realize that this is really equal to x squared. The only root of x squared is 0. This means that the only eigenvalue of A is 0. So in step 2, we only need to find a basis for one eigenspace of A, since A only has one eigenvalue. So now we will find a basis for the 0 eigenspace of A. This is the same as finding a basis for the kernel of A minus 0 times the identity matrix, but this would just be the 0 vector. So this whole thing is just A. So we're just looking for the kernel of A. So we take this matrix and put the 0, 0 into an augmented form, we will then row reduce and solve for x and y. We see that the first column has a leading one. The second column does not have a leading one. So we set the second variable to a parameter. I then turn this into an equation and do back substitution. I replace this y with t. So x is equal to t. I can then write a general solution to the kernel of the matrix. I can then take this vector in the set containing just this vector is a basis for the 0 eigenspace of A. That was step number 2. I will now do the third step. The only vector I get from step 2 is this vector. So I form a set consisting of just that vector. And I see that this has fewer than 2 vectors, but the matrix has width 2. So no eigenbases exist for this matrix. Sometimes we just want to know whether a matrix has an eigenbasis without needing to actually find an eigenbasis. So this formula helps us with that. A matrix has an eigenbasis if and only if the width of A is the same as the sum of the dimensions of all eigenspaces of A. This notation, E sub a number of A, is a shorthand for the eigenspace for that number. And the reason why this works is because a basis for the lambda eigenspace of A has as many vectors as the dimension of the eigenspace of A. For example, if I have a matrix that is 4 by 4, and I know it has exactly 2 eigenvalues, lambda 1, lambda 2, and I was able to compute the dimension of both eigenspaces, and I see that they both have dimension 1. And if I compute 1 plus 1, that is equal to 2, which is smaller than the width of A, which is 4. So without having to go through the calculation, I can conclude that A has no eigenbasis. In this exercise, let's try to show that this matrix has an eigenbasis without actually finding one. And here I will tell you that A has 2 eigenvalues, exactly 2 eigenvalues, 1 and 7. Let me give you a hint. Compute the dimension of both eigenspaces, but without actually finding bases, and then use this fact number 3. So first, I will find the dimension of the one eigenspace of A. It's possible to just find the dimension sometimes without actually computing a basis. So I will try to just do that. Remember that the one eigenspace of A is the same as the subspace, which is the kernel of A minus 1 times the identity matrix. This is 2 minus 1, and 2 minus 0, 1 minus 0, and then 2, 5 minus 1, 2, 1, 2, and 2 minus 1. This gives me 1, 2, 1, 2, 4, 2, 1, 2, 1. I see that each row is a multiple of all of the other rows. So this tells me that the rank of this matrix is 1. Knowing the rank of a matrix is helpful because of the rank nullity theorem. It says that the rank of a matrix plus the dimension of the kernel of the matrix is equal to the width of the matrix. And we know the rank of this particular matrix, and the width is 3. So that tells us that the dimension of the kernel is 3 minus 1. So this gives me the dimension of the one eigenspace of A, which is 2. Next, I will compute the dimension of the 7 eigenspace of A. The definition of dimension is the number of elements in any basis of the subspace, but sometimes it's possible to compute just the dimension without actually computing a basis. So I will try to do that. Since 7 is an eigenvalue of A, an eigenvector for the eigenvalue 7 does exist. So this space contains a non-zero vector. But from an earlier lecture, we learned that the only subspace with dimension 0 is the 0 subspace. All other subspaces have dimension 1 or higher. This tells us that this subspace, because it has a non-zero vector, must have dimension 1 or higher. So we will apply fact 3, where I sum the dimension of all eigenspaces of A. I compute earlier that the dimension of the one eigenspace of A is 2. And just now, we saw that the dimension of the 7 eigenspace is at least 1. So this sum is equal to or greater to 3. And so A has an eigenbasis because the width of A is 3. This argument that we use here is something that we can use in general. So we can say that the dimension of any eigenspace of A, if the eigenvalue is an eigenvalue of A, must have dimension 1 or bigger. So in general, we can say that if a number is an eigenvalue of a matrix, then there is at least one eigenvector corresponding to that number. So the eigenspace for that number has dimension at least 1. And so a basis for that eigenspace has at least one vector. So each distinct root of the characteristic polynomial guarantees at least one vector in our potential eigenbasis. This gives us this theorem. If an n by n matrix has n many distinct eigenvalues, the matrix must have an eigenbasis. It doesn't work the other way, quite the same way. So if an n by n matrix has fewer than n distinct eigenvalues, it may have an eigenbasis or it may not. We need to use like algorithm 2 or a different method to find out for sure. But if we know that the matrix has n distinct eigenvalues, then we can immediately say that it has an eigenbasis. In this exercise, let's try to determine whether this matrix has an eigenbasis using what we have learned so far. My hint is to first just compute the eigenvalues and then use the theorem we just saw. First, I compute the characteristic polynomial of A. So I have the determinant of x times the identity matrix minus A, which gives me this matrix. Because of these 0, 0, I believe it will be easiest for me to do cofactor expansion along the second row. So I take this value x, and then I have to compute the sign. So I have -1 to the power of 2 plus 2, because x is in position 2, 2. And then I compute the determinant of the smaller matrix, which I get by erasing the entries in the same row and column of x. So I erase these entries. So I get x times x minus 1 times x minus 1 minus 3 times 1. So I get x cubed minus 2x squared minus 2x. And next, I will compute the roots of this polynomial. I notice that x is a factor of this polynomial. So one of the roots of the polynomial is 0. The other two roots are roots of this factor. I don't see a quick way to do factorization here, so I can use the quadratic formula or complete the square, I have the negative of -2 plus or minus 4 plus 8 divided by 2. So I get two other roots, 1 plus square root of 3 and 1 minus square root of 3. Since a has three distinct roots, 0 and these other two values, we can use theorem 4. Since a is 3 by 3 and has three distinct eigenvalues, a must have an eigenbasis. We have a theorem which tells us the lower and upper bound of the dimension of an eigenspace of A for an eigenvalue. We have seen earlier that the lower bound is 1, but here the theorem says that an upper bound is the number of times that x minus that number lambda appears in the factorization of the characteristic polynomial. So if this number lambda is a root of the characteristic polynomial, the number of times it appears is called the multiplicity. So let's say it appears m times. Then the dimension of this eigenspace is between 1 and m. This gives us two different ways to count an eigenvalue. If we care more about the geometric interpretation, then we can think about this geometric multiplicity, which is the dimension of the eigenspace. We can also count eigenvalues by counting how many times x minus lambda appears in the characteristic polynomial. And this number is called the algebraic multiplicity. The connection between the two, the geometric multiplicity and algebraic multiplicity, is given here. So the geometric multiplicity is smaller or equal to the algebraic multiplicity and not the other way around. This is the end of lecture 15b. Next time, we will talk about an application of eigenbases, which is a way to diagonalize a matrix if that matrix has an eigenbasis. Thank you for listening.